So I'm going to talk today about water storage, land water storage and global hydrologic and land surface models, and comparing with GRACE satellite data. A lot of interest these days in using remote sensing global models. I know a lot of you from the posters and everything are working on local scales, and they're probably allergic to this, as a lot of hydrologists are. And I get... After AGU a couple of years ago, I heard some people, hydrologists, saying, well, with the global modeling and remote sensing, I don't need to monitor anything. And, you know, that is not the message that we want to give. I mean, these are nice tools, and we want to look at things from a variety of scales, but we don't want to stop monitoring either. But in the US, NASA has a very strong PR program, and so, you know, some people may get that impression that we can do everything from space. This work that I'm just going to describe today did with a collaborative effort with people that work in GRACE satellite data, Himanshu Savi, David Weiss, and Mike Croteau, and then a lot of the land surface modelers and hydrologic modelers. So I'm very grateful for their collaboration and for their input. I always want to make sure that I'm representing something correctly, so I like to work with people who developed the work originally. So I'm going to give you some background on GRACE satellites and global models, and Reid gave a very nice intro for some of this, so I can probably speed through some of that. And then I'm going to compare the modeled water storage. I'm going to talk about storage rather than fluxes, because we get storage from GRACE. How many of you here have heard about GRACE satellites? Okay. How many of you think it's a religion? No. It was launched on St. Patrick's Day in 2002, so it might be considered March 17th. So, so if you've heard about GRACE and you saw the recent launch of the GRACE follow-on, maybe the original experiments were estimating the distance between the satellites and the ground surface, and when you go over regions of high mass or wet areas, the distance decreases because of gravitational attraction. So if you measure those distances, then you can look at changes in water storage. The reason hydrologists are a bit allergic to GRACE satellites because it's coarse resolution, as Reid mentioned, about 100,000 square kilometers. And they would like to apply it to watersheds that are gnat's ass, you know, so you just can't. But it's like a parent with kids. You always want it to do what it can't do. So really, we should take advantage of what it can do and not try to force it to do other things. So the original GRACE mission was supposed to last 5 years, was launched in 2002, but it lasted until 2017, and eventually the satellites dropped out of the sky. GRACE follow-on was just recently launched, and everything seems to be going great. It takes about 90 minutes to complete one circumpolar orbit, and they provide data at monthly timescales. 1 gigaton mass change is 1 cubic kilometer of water storage change. And it's one of the only satellites to penetrate deep in the subsurface, so it estimates total water storage from the atmosphere to the MOHO. And then they subtract the atmospheric component, and you're left with snow, surface water, soil moisture, and groundwater. Some people, it's 2 satellites. It's more accurate to estimate the distance between 2 satellites and look at the changes in those to figure out changes in water storage. And some people use the analogy to Tom and Jerry with these GRACE satellites following each other. So I'm hoping this will work.
Gravity. It's everywhere. It's the force that keeps our feet on the ground and the moon orbiting Earth. But where does it come from? Mass. That's simply the amount of stuff that makes up an object. The more mass something has, the more gravity it has. Earth's gravity is constantly changing because something with a lot of mass is moving around all the time. What's moving? Water and ice. If you've ever picked up a bucket of water, you felt just how much mass it has. It creates a lot of gravity. Using satellites, NASA can measure Earth's gravity like a scale in the sky. By comparing one month to the next, we can track where the water and ice is going. Weaker gravity means there's less water in that spot. This can tell us where a glacier is melting or a severe drought is drying up lakes. And stronger gravity? more water such as in the rainforest in the Amazon. Our scale in the sky even lets us measure water deep underground. Knowing where the water and ice is moving helps us improve weather models, forecast droughts, floods, and wildfires. It also helps us get water where people need it. Measuring gravity from space helps NASA better understand the entire water cycle here on Earth. And that can come in handy next time you want a glass of the stuff.
So basically, you're measuring the distance between these two satellites. They're about 220 kilometers apart, and you can measure the distance to submicron level. And so when you have these satellites approaching an area of a wetter area or an area that's getting wetter, then the leading satellite speeds up. Because it's of gravitational attraction, and so the distance between the two increases, and then as they are both equidistant from that wet mass, then the distance decreases, and then eventually the trailing satellite speeds up. And so measuring the distance between the satellites then gives us changes in water storage. So recently somebody said, how can you get the total water storage? You can't from GRACE. You can just get changes in water storage. And to tell you the truth, I don't think total water storage is that important, because in many cases in groundwater systems anyway, you can't use most of the storage because you disconnect with surface water and all that sort of thing. So anyway, this kind of gives you an idea. So by measuring the distance between the satellites, GRACE estimates changes in gravity. Time variations in gravity changes are mostly related to changes in water distribution, ice melting or droughts or floods. And it estimates total water storage. A lot of times, you have papers talking about groundwater storage, but to estimate the groundwater component, you need to subtract the other components that you get from other data. It's low resolution and can only be applied at large scales. Even though they provide gridded data at 1 degree resolution, you need to aggregate those grid cells to about 100,000 square kilometers. So 1 gigaton mass change is equivalent to about 1 cubic kilometer of water. So that's GRACE, which gives us data on water storage changes over the period that we have GRACE data. And a recent paper that came out in Nature by Matt Rodell and others says, well, some of these trends that we saw from 2002 to 2017 may be indications of long-term trends up to 2100. I think, we're really looking at decadal change over that time scale, and whether it continues or not is questionable. So the models then, we need models to make projections, to look at, people use them to look at the impacts of climate change and human water use. And this is Yoshiwada's groundwater depletion, as somebody showed earlier. So a lot of groups are relying heavily on these global models. So it's very important for us to understand how reliable they are. UNESCO World Water Assessment, global assessments of water resources. And then models have also been used to evaluate the impact of land water storage changes on global mean sea level. Global models, basically we're looking at precipitation as the main input, and the outputs, evapotranspiration, runoff, water extraction, equal to changes in total water storage. And so we accumulated the water storage from the different components in the models then to estimate total water storage to compare with GRACE. And then we use other sources of data. If we want to look at groundwater storage changes, then we subtract these other components, snow in the US from SNODAS or from models, surface water storage from reservoir monitoring, or soil moisture storage mostly from land surface models. And then there are a variety of land surface models. Reed mentioned that he used a CLM linked with his model, and we've NOAA, Mosaic, VIC, CLM, Catchment Land Surface Model, CLSM. So there are two basic types of hydrologic models, global hydrologic models, or what some people call global hydrologic and water resource models. These are sort of accounting models, and they were originally developed to look at water scarcity issues. And these include water gap, global hydrologic model, or PC raster, global water balance. So their daily water balance models include all the different storage compartments, surface water, soil moisture, and groundwater, and include human water use, reservoir storage, and human groundwater abstraction. The other models that Reid talked about were land surface models. These were developed more by the climate community to provide the lower boundary condition for climate models, more physically based and mostly include energy budgets, but most of them just include snow and soil moisture compartments. They don't include surface water storage mostly or groundwater storage. CLM does, but most of the others don't. And they don't include human water use. So here you can see some of the model attributes, and these are the models that we are going to compare. So two global hydrologic models, WGHM and PCR, forced with the same precipitation data and include all the storage compartments and number of soil layers and soil thickness. These are the land surface models, VIC, NOAA, CLSM, and CLM. These mostly just contain soil moisture storage. Some include groundwater storage and don't include surface water routing and can include a variable number of soil layers with different thickness. And only one of these models, WGHM, is calibrated to long-term average flow in rivers. So I'm going to look at a couple of different things then. What is the relative contribution of different signals to the total signal? What is the relative contribution of seasonal signals, trends, interannual components to the total signal that we see from models and GRACE? Do you guys have any ideas which would be the most important component if you disaggregate the time series into those different components? Pardon? Oh, the tide? Oh, well, I mean, I'm just talking about the time series of the land hydrology. Do you think trends are more important, or seasonal signals, or interannual, or seasonal? Okay. How do model storage changes compare with those from GRACE? So GRACE, you know, it's at a 450 kilometer elevation, so it's like another set of eyes or a weighing scale in the sky. If you think of it as a set of eyes, it's got cataracts, you know, it's filtered, it's blurred vision, you know. So then do you think the modeled water storage changes would be less than or greater than GRACE water storage changes? Greater, okay. We'll just see. Then impact of land water storage on global mean sea level. Any ideas about that? Last IPCC, they said it was too inaccurate to evaluate. Do you think land water storage contributes positively, say results in an increase in sea level rise, or negatively decrease the rate of sea level rise? Negatively, okay. And then we'll talk a little bit about differences between models and GRACE. So a lot of people zone out in my talks, and they say, you know, I read a book recently, it was called Twin or something, said 3 o'clock in the afternoon, worst time. You have people who are good in the morning, people who are good at night, but nobody's good at... So assuming half of you zone out, I give you the main points now. So the seasonal signals are dominant, 50 to 75% of the total signal based on the ratio of the variances for both GRACE and models. The trends, less than 5%. But a lot of times we're talking about what are the trends up to 2100, you know, what's going to happen and stuff. So a lot of times we're interested in trends, but it's the smallest part of the signal, so it's the most challenging. How do model storage changes compare with GRACE? They underestimate the trends, and they do a better job of the seasonal amplitudes. So, and that varies with latitude that I will describe. The human intervention, this would be reservoir storage and groundwater abstraction. So it amounts to about 56 to 86 cubic kilometers per year based on WGHM and PCR. And this is in the trends, but does not affect the seasonal amplitudes at the basin, at the catchment scale. Impact of land water storage trends on global mean sea level. So what we found from GRACE data between 2002 and 2014 was the land water storage increased over that time by about 70 to 80 cubic kilometers per year. So with land water storage increasing, then that would be a negative contribution to global mean sea level. So it would reduce the rate of sea level rise by about 0.2 millimeters per year. And the models indicate the opposite trends, minus 450 to minus 12 cubic kilometers per year. And the differences between the models and GRACE, a lot of potential differences, very difficult to isolate these. But I think some models missing storage compartments, limited storage capacity to accommodate the range in storage that we see from GRACE, and uncertainties in fluxes. So we used 6 different models, 2 hydrologic and 2 land surface models. We focused on trends and seasonal signals, and we used several different GRACE solutions, mostly the recent Mascons solutions, which have increased signal and less leakage. And then we compared then these with total water storage trends and seasonal amplitudes from the models by summing up these components, or whatever components the models have. So we looked at 186 river basins globally, and here we show the colors reflect the climate in the different regions, blue being humid and yellow being arid. And I'll talk a little bit about some of these basins: Amazon, Arkansas, Okavango, Euphrates, Ganges, and Murray, and the High Basin. So the first question then is, what's the relative contribution of the different signals? And this is based on GRACE Mascons solution. And this is for the 186 basins. And the blue is, we did STL, seasonal trend decomposition with the lowest. And so the blue is the long-term trends, the green is the interannual, the orange is the seasonal, and gray is the residual. And so what we found for this Mascons solution is that the trend is 4%, interannual 13, seasonal almost 70, and residual 9. So the seasonal signal is dominant, but in semi-arid regions it's not as high. But in all other areas it's greater than 60%. GRACE data 50 to 70%, models 60 to 75% of the total signal. And so here we show the percent of the signal. So you see in most areas it's greater than 60%. Most of the regions are red, except in the semi-arid regions where it's blue. And it's a low percentage because interannual is important. The magnitude of the seasonal signal is highest in the tropical basins, the Amazon, the in this region here, Niger in the Indus-Ganges, Brahmaputra region, and then is high in some of the high latitude basins, but low in the semi-arid regions. So that was the first question. Seasonal signal is dominant, as you guessed, and then seasonal amplitude highest in the tropical basins. So model water storage changes compared to GRACE. So this is the trends from GRACE between 2002 and 2014, because we only have models up to 2014. So the blue are increases in storage in cubic kilometers per year. For example, the Amazon, this is GRACE, Amazon about 40 cubic kilometers per year, the largest basin, 6 million square kilometers. And the red areas are declines in water storage. The Ganges about minus 12 cubic kilometers per year. So when we sum them all then from GRACE, we get a net increase in land water storage of 70 to 80 cubic kilometers per year. And when I show you the models, the land surface models down as low as minus 450, and the hydrologic models, WGHM minus 12. So this is GRACE in the center, and these are the models. And here we're looking at the Mississippi Basin. The first 3 are GRACE data. So you have some variability in GRACE solutions in different basins. These are the hydrologic models, and these are the land surface models for the Mississippi. And this is the trends over 2002 to 2014. So GRACE Mascons showing an increase, the hydrologic models variable, and the land surface models. GRACE more uniform because the Amazon is such a large basin, and GRACE does well with large basins. The hydrologic models, PCR minus 70, minus 60 something. And then some of the land surface models, all declines in storage, and this is the order in which we're showing them. The Okavango region, which is an internally drained basin, GRACE showing an increase in water storage in response to wetter conditions. The hydrologic and land surface models greatly underestimating this because the runoff is just goes away. They don't accumulate water storage in endorheic or internally draining basins. The high basin decreases in water storage from GRACE because of human water abstraction. This is the only basin where we see the hydrologic models overestimating the declines in storage. Land surface models, no trend because they don't include human water use. And the Ganges then again decline in storage related to human water use. Hydrologic and land surface models are variable. So if we look at the global maps then, so this is the hydrologic models. These are both forced with the same precipitation data and same model structure, and this is the GRACE. So you can see even comparing WGHM and PCR, quite large differences in the Amazon and some differences in the Ganges and other basins, and then differences with GRACE. So these guys had not compared their models beforehand, so we're a little bit surprised at the differences. And these are the land surface models. So the red are declines in storage, and the blues are rises in storage, and the yellow is where it's close to 0. So it's saying it's agreeing with more with GRACE. So this is the NOAA 3.3. So you can see a lot of red. So underestimating water storage trends relative to GRACE. And the CLM4 then does a much better job. It has surface water storage, groundwater storage, but it still underestimates, for example, in South America and other regions. So this is the correlation between water gap and PCR relative to GRACE. Very low correlation coefficient, R-squared 0.1 to 0.03, and low slopes indicating overall underestimation relative to GRACE. And this is NOAA and CLM. Again, R-squared 0.04, 0.05. So almost no correlation with GRACE. So the models are underestimating the rises in water storage during wet periods and declines in water storage related to droughts and also to groundwater abstraction. So we can also look at the time series in data looking at the Ganges, and you can see the black line is GRACE and the colored lines are the models. So you can see a decline in water storage with GRACE and then leveling off. The models start off low and end up high, so opposite trends with some of the land surface, with some of the models. And the same Indus, they're always, nearly always underestimating the declines in water storage relative to GRACE. And this is the uncertainty in GRACE from the variability among the solutions. The Arkansas, again, underestimating the decline. And then the high basin, the hydrologic models are overestimating the decline there, and the land surface models underestimating. So these are all underestimating related to human water use in these basins. And the Euphrates drought, 2007 to 2009, and the models are just flattered. They're just not getting that drought. And we haven't seen a recovery from that drought over this time period. So these are all declines in water storage related to drought or human water use. So then looking at the Amazon, the black, we see a great increase in trend, about 40 cubic kilometers per year, and all of the models underestimating that increase. The Missouri, again, underestimating the increase in water storage in response to wet periods. The Okavango, just flat. The models are flat, whereas GRACE shows an increase. And the Murray-Darling Basin, this is an increase related to flooding at the end of the millennial drought. And the models do a fair job of responding to this, but again, slightly underestimated. So let's look at the seasonal amplitudes then. The models do a better job of the seasonal amplitudes we're seeing. So this is the WGHM and R square of 0.6. So some basins, this is the 1-to-1 line, overestimate the seasonal amplitudes, and some basins underestimate. And this is CLM4, does R square 0.79. So a much better job of the seasonal amplitudes than the trends. We see the trends as the small signal. So again, here we're looking at the ratio of the seasonal amplitudes from global hydrologic models versus GRACE. So yellow colors mean that it's close to GRACE, close to 0, and then blue means that the models are overestimating, and red means underestimating. So underestimating in tropical basins and overestimating in some high latitude basins. And PCR, more yellow, does a better job. Hydrologic models underestimating in the tropics and overestimating in the northern high latitudes. And CLM again does a much better job with the seasonal amplitudes, but again this other, so the 3 of the 4 land surface models greatly overestimate in the northern high latitudes. So if we look at, I think I'm going to, I'm running out of time, so I think I'm going to skip this. Well, this is the southern hemisphere, -45 to -20. This is the seasonal amplitudes. You can see the models underestimating relative to GRACE. GRACE is the first one, and this is the percent bias in these different models. Underestimating in the tropics for most models, except PCR and CLM. And the northern mid-latitudes, they do a good job, and the northern high latitudes, they overestimate the seasonal amplitudes. And here just some seasonal annual signal. For example, the Amazon, black is GRACE, and the models are not getting the timing quite right and underestimating the highs and lows. And similar with the Ganges. And the northern high latitudes, they're overestimating the amplitude relative to GRACE. More snow, and so the next thing is the human intervention. What impact does that have? So that includes reservoir storage and groundwater abstraction. So here we run WGHM with human water use and without human water use. So if there was no impact, it would plot along the 1-to-1 line. But these basins, then we see the impact of human water use. And when we add it up, we get -56 cubic kilometers per year because of groundwater abstraction. And PCR -86. So 56 to 86 over these basins. And it's important then what's causing this human, you know, a lot of times in a lot of papers, GRACE total water storage declines were attributed to human water use. And I think it's important to understand whether it's human water use or whether it's climate variability, because that impacts how we're going to manage the system. So for example, in the Colorado River Basin, an early paper suggested by Castle and others indicated that groundwater depletion during drought was accounted for 80% of the storage decline, and they attributed most of that storage decline in the Colorado River Basin in the US to human water use of groundwater. And so we went back and reevaluated that and found that in the upper Colorado Basin, it was mainly surface water storage and soil moisture. And in the lower basin, there was some groundwater storage, but it was mostly in response to climate. And these are the hydrographs in the lower basin, so they're all pretty flat. So this is the Colorado River, this is Arizona, this is the lower basin. So what's been happening is that they have been transporting water from the Colorado River to the cities like Phoenix and Tucson through the Central Arizona Project, and they have managed aquifer recharge. They changed irrigation from surface water to groundwater, so they've been recharging these depleted aquifers. And these are the spreading basins where they apply the surface water to recharge the aquifer. And so in these active management areas, then in Phoenix and Tucson and areas, these are the long-term mean hydrographs over thousands of wells. You can see that the water storage has increased and stayed fairly stable over the GRACE period. So we didn't see declines in water storage. The only place we see declines in water storage is where we have basins that don't have access to surface water and they can only use groundwater. And so we need to understand the system better than just blindly saying it's groundwater storage. And I really like this study by Petrodol, where she looked at net abstraction. So negative values indicate increases in groundwater storage as a result of surface water irrigation. So these blue areas are where they're irrigating with surface water and recharging groundwater. So I think to have more sustainable development in the future, then we have to have conjunctive use of surface water and groundwater where we can, and then managed aquifer recharge from wet to dry periods. So this is the impact of human intervention on seasonal amplitudes. So this is with human intervention and without. So do you think human intervention impacts seasonal amplitudes? No, right. I mean, it's mostly on the one-to-one line. So we don't, at the basin scale, then we're not really seeing the impacts of human intervention. Net impact on global mean sea level. Yeah, okay. I got 5 minutes. So we saw that GRACE showed a net increase in water storage over all of the basins of about 70 to 80 cubic kilometers. So that would negatively contribute. Dividing that 70 to 80 by 60, the area of the oceans, then gives us the global sea level. So that would contribute negatively to global mean sea level. So GRACE responds to human intervention and climate. We can isolate the impact of climate by comparing the models run with and without human intervention, and we get this contribution. So the human intervention decreases land water storage, so that contributes positively to sea level. So subtracting this from this, then we get the climate contribution. And you can see that the natural variability in climate over this decadal time period then is about 2 times the human intervention at the global scale. So what's causing the differences between models and GRACE? So I think we're looking at storage. So land surface models, many of them are missing surface water storage and groundwater storage. Underestimation of seasonal amplitudes in tropical basins may be because we're missing surface water storage and overbank flooding. And also the storage capacity in these models is limited, so it's not large enough to accommodate the range in water storage that we're seeing from GRACE. Then also fluxes. If we overestimate the storage change, it might be because we're overestimating the precip input or underestimating the outputs like ET or runoff. So variations in precipitation input. In the northern high latitudes, different models have different snow routines, frozen soil. And in arid basins, I think it may be overestimation of evapotranspiration. So the follow-on mission is the same, at the same elevation, so we'll have essentially the same resolution. It won't be a higher resolution. Why didn't they put it in at a lower elevation and get higher resolution is because that would limit the lifespan of the satellite. Gochi's satellite was about half the elevation of GRACE and had a much shorter lifespan. So what should we do about global modeling? We need to consider in the future both the fluxes and the storage, and maybe we should use multi-model ensembles rather than relying on single models. As you can see, there's a lot of variability among the models. And then maybe we need to develop these models for regional areas like the Amazon or the northern high latitudes or where there's a lot of human intervention, and then aggregate those to the global scale. Should we calibrate models? Some studies have shown with the fluxes that they didn't really get any better results with calibrated models. And then, like Martin Clark and others, are using single models and changing processes to isolate controls on differences. So we're working with the USGS Powell research study with USGS and NASA to look at the US, where we've got a lot of data, and we should be able to get more information comparing the regional models that the US develops for the Central Valley and other areas with the global models and with GRACE. And I mean, the USGS spends years developing, say, for example, the model for the Central Valley. And so I think this would be important. So I've already gone through these. The seasonal signal is dominant. Model storages are underestimated relative to GRACE. Human intervention depletes groundwater storage, and saw the impact on the global mean sea level, and talked about some of the causes of differences.
Land coverage, for example, deforestation, which could also affect gravity, or
yeah, I mean, GRACE just sees the water storage changes, and so whatever causes that, then it picks it up, you know. So in response to climate variability, land use change, water abstraction, or any of these different things, but at a large scale. Go ahead. Well, GRACE is gospel, right? We did look at a lot of the uncertainties in the GRACE data, and when I showed the time series, I showed the gray area around GRACE to show the uncertainty, so the models are way outside those bounds. And for the seasonal amplitudes, we also looked at the variability among the GRACE solutions. And so GRACE is really good at large scale. So for looking at the contribution of land water storage to sea level, GRACE is perfect, you know, but models are not. And many of these basins, I mean, the Amazon, 6 million square kilometer area, you know, I think, and we saw that the GRACE data showed pretty uniform results, and the models were underestimating. So yes, when we had the reviews through this, we had to go through all of, you know, measurement errors, leakage errors, all sorts of things with the GRACE data to show the uncertainty. Go ahead. Can she ask? Right. So two questions. So can GRACE and the model see the managed aquifer recharge that we had going on in the Colorado? So as I said, the earlier studies said attributed, they just saw the changes in storage. Then we have to figure out where is that storage changing occurring. Is it in the reservoirs? We have two of the largest reservoirs in the US in the Colorado Basin. So there was some changes in reservoir storage, and then soil moisture, and how much of it was groundwater. In the upper Colorado River Basin, there's very little groundwater use, and the USGS has estimates of that. So we knew, and then the hydrographs were flat. So there wasn't really much groundwater storage change. In the lower basin, there is some groundwater storage change. We had about 1,000 hydrographs. We had ground-based gravity, and we saw that in most areas there was some groundwater storage change in response in areas that weren't being pumped. So that's in response to natural climate. And then in the areas where you would expect a lot of depletion, like Phoenix and Tucson, where they've had depletion decades in the past and subsidence and everything. So they have corrected that with this active management process where they're doing irrigation with surface water. The Central Arizona project finished in the 90s, and irrigating with surface water and managed aquifer recharge. So it doesn't get into that detail, but I mean, so we have to understand what's causing the changes. And so with doing that, looking at the ground-based data, then we could evaluate that. And your second question was, Oh yeah, so the modelers are starting to consider storage a lot more. In the past, they've looked at fluxes, runoff, ET, compared with runoff data from the GRDC database. Now they're looking at fluxes. And so WGHM sent me recently model simulations where they had changed the soil moisture storage capacity and whether they were getting improved seasonal amplitudes or not. So yes, and then in the Easy MIP model intercomparison project, they're now collecting storage data and using that as one of the parameters to evaluate.